What happens if you fall into a black hole? If you turn around near the edge of a black hole, you'll see 100 reflections of yourself. That's not magic. It's the photon sphere. And in about 15 seconds, not even light will be able to escape your eyes. Today we're diving into a wild topic. What would happen if you were thrown into a black hole? And no, this isn't science fiction. It's all grounded in hardcore physics. Before we toss you in, let's quickly go over what a black hole actually is. Even Einstein himself once described black holes as where God divided by zero. He didn't believe they could really exist in our universe. But well, we found them anyway. When extremely massive and dense stars reach the end of their lives, they go through a dramatic transformation. They collapse entirely, leaving behind nothing. What's created is called a singularity, a point in space-time said to have infinite density and therefore infinite gravity. Einstein's general theory of relativity gave us a revolutionary idea. Gravity isn't a force acting on objects. It's the result of space and time being warped by mass. It explains how the Earth orbits the Sun and how planets move like they're spinning around their own cosmic homes. Inside a black hole, there's no solid black surface. The singularity hidden within is so dense it severely distorts space-time, forming a deep well with vertical walls. In 1939, Einstein even published a paper arguing that stars collapsing into singularities couldn't happen and wouldn't happen in our universe. But in that same year, Robert Oppenheimer, yes, that Oppenheimer, and physicist Hartland Snyder published a paper predicting that stars could indeed collapse under their own gravity to become black holes. So back to you, what would actually happen if we tossed you into a black hole? One of the strangest things about black holes is that anything can become one: stars, planets, or even tiny humans like us. As long as you can be compressed down to within your Schwarzschild radius, you can become a black hole. German physicist Karl Schwarzschild was the first to find an exact solution to Einstein's field equations, and it was a simple yet beautiful discovery. Take our sun, for example. If you compressed all its mass into a sphere about 1.86 miles in radius, it'd become a black hole. As for Earth, you'd have to compress it down to a radius of just 0.35 inches, about the size of a marble. And for a human, well, you'd need to be squeezed down to way smaller than a proton, an unimaginably tiny point. But if you could be compressed that far, congrats, you'd be a black hole too. Now, which black hole should we throw you into? We could pick a small one, but that'd be boring. Let's go bigger. Some black holes are so massive they outsize our entire solar system, weighing in at billions of times the mass of our sun. But okay, let's pick one that's a bit closer to home. Sagittarius A*, the supermassive black hole at the center of our galaxy. You're actually orbiting it right now. It's also one of only 2 black holes we've actually photographed. Now let's set the scene. Let's say you and I fly out there in a spaceship. We park it about 620 billion miles from the event horizon. I'm staying on the ship to observe. You're taking the plunge. Here's the thing. General relativity says that time passes differently near a black hole. The closer you get, the more space-time gets warped. You saw this in Interstellar, and it's real. To track the experience, I'm giving you a special watch. It shows 2 time readouts, one from your perspective and one from mine watching from the ship. We sync the watches and your black hole journey begins. As you start falling, you'll see the black hole devouring matter from afar. The scene is breathtaking. Friction heats the matter to extreme temperatures. If we tried to simulate that on a regular laptop, it would take over a decade. In real life, the accretion disk glows blue or even white, but our simulation shows it in orange to make it easier to observe. You check your watch, 30 minutes have passed, but you've only traveled 0.1% of the way toward the event horizon. Meanwhile, I've experienced just 11 seconds more than you. The time difference isn't huge yet, but as you get closer, things start to get weird. Space-time warps harder, and light coming from behind or beside the black hole bends around and hits your eyes. You're seeing light from behind it bent by gravity. After 2 hours, you've completed 1.4% of the journey. I'm now about 44 seconds ahead of you. That's unsettling, but still manageable. The black hole's shadow, the central dark spot, is growing faster than expected. That's the gravitational lensing effect. It's curving all the nearby light rays inward. A long time passes. You check your watch again. From your perspective, you left 12 hours ago. But from my ship, I've been watching you drift toward the black hole for nearly 15.5 hours. Now you're really close. Things are about to get seriously strange. Right before reaching the point of no return, you'll pass through a place so bizarre and unique, it'll blow your mind. Welcome to the photon sphere, one of the weirdest regions in the known universe. Here, gravity is strong enough that photons, light particles, can orbit the black hole. They're not being emitted or reflected, they're just stuck in orbit. If they move at the perfect tangent to the black hole's surface, they circle it. But if they deviate even a little, they fall in or fly away. Now imagine this. If you're momentarily frozen in the photon sphere and look around, you'll see something wild. Your own back. Multiple copies of your head, all facing the same way, all gazing at space. You're seeing your own back like someone's standing right next to you. No tech required. Just space-time messing with your view. As you continue your descent, the black hole takes up more and more of your vision. It feels like the darkness is swallowing you. Why? Because that black shadow isn't just the front, it's the back and sides too, all warped into view. You've been falling for 13 hours now. In 24 more minutes, you'll cross the event horizon. But from the ship, I've been watching your fall for almost 20 hours. Another 18 minutes go by. You check your watch again. From your view, only 18 minutes passed. But I've been watching you for 18 full hours. Now we're approaching the final moment. Just 6 minutes left before you cross the event horizon. You close your eyes, take a deep breath, check your watch, but it looks broken. It says I've been watching you fall for infinity. But it's not broken. That's just physics doing its thing. From the ship, I've watched you fall for decades. You turn red, gravitational redshift. I can only see you now in infrared. And even if I lived forever, I'd never see you actually cross the event horizon. From my perspective, your final 6 minutes last for eternity. Sounds like sci-fi, like a dream. But it's not. It's pure Einstein. And now you're inside the event horizon. What happens in there? Strangely, it's hard to tell when you crossed it. You can still see the universe outside. You might even see my ship floating in the distance. But all that light, just like you, is falling inward toward the singularity. You've crossed the point of no return. Where density is infinite. Where our physical laws break down. Where time stops. To escape, you'd have to move faster than light. And we both know that's impossible. A common misconception is that as you look outward, the extreme time dilation will show you the entire future history of the universe. But that's not really how it works. As you approach the singularity, the universe outside compresses into a thin, glowing ring. And then comes the final moment. Your feet stretch out in front of you. Your body elongates in a process called spaghettification. You become one with the black hole and drift across the cosmos forever. It's spine-chilling just to imagine, but you can't help wondering what it'd be like. Black holes, terrifying, beautiful, and impossible to look away from.